We always love to hear from you. Send us your views, comments, and videos with your name and town to the One Africa TV's WhatsApp on 081-200-6659 or send an SMS to 555. One Africa TV. It just gets better.
With trusted quality and great value on all Clicks brand products, switch and save. Buy any 3 Clicks razors or blades, cheapest one free. Buy AfriTrue shampoo or conditioner 1 litre, 2 for $97. And buy any 3 bathroom cleaning products, cheapest one free. Or buy any 3 Clicks antibacterial cleaning products, 750 mils, cheapest one free. Clicks. Feel good, pay less.
Lesson. And here in this table, here on the left in this column, I have placed the halogens as they appear in the periodic table. The first is fluorine, then chlorine, bromine, iodine, and astatine. Astatine is also there, just to remind us that they are more. All right. So let us talk about their properties now. Let us start from their physical properties. First of all, what are the physical properties? It's like melting and boiling point, and in which state they are, and how reactive they. Well, this is a chemical property. Now, considering that we have this table in front of us, the first column here actually is about reactivity, which is not a physical property, it's a chemical property. So the reactivity of these metals, look at this. As we go down the group from fluorine towards astatine, the reactivity decreases. In other words, the ones at the top, like fluorine and chlorine, are the most reactive elements in this group, which is in contrast with what we saw in the alkali metals and the alkaline earth metals. In these groups, group 1 and 2, as we go down the group, the reactivity would increase. They would become more reactive. But here is the opposite. Down the group, the reactivity decreases. The ones at the top are more reactive than the ones at the bottom. Now, why are they so reactive? Because from their placement in the periodic table, we can understand that in terms of the electrons that they have in the outer energy level. Being elements of group 7 means that they have 7 electrons in their outer energy level, their outermost energy level. All of them have 7, including the last 2 that we're going to ignore. All of them have 7 electrons in their outer energy level, which means in order for them to complete the energy level, they only need 1. So it's very easy to find another element, another atom that has an extra electron to give away and for them to pick it up. So we can see that this group 7 element react very easily with elements from group 1 and also from group 2. Because elements which are metals from group 1 and 2 find it easy to give 1 or 2 electrons. And elements from group 7 find it easy to pick up 1 electron. So halogens, in other words, react very easily with the alkali metals in the alkaline earth. metals, because they only need one electron to complete the outer energy level. They can pick it up easily. It's easy to pick up just one electron. And once they have completed their outer energy level with 8, they become stable. That is the idea in these reactions when atoms of different elements react with one another. They try to become more stable, because once they are more stable, they have less energy. And in nature, the most stable condition, the most stable state is where you have as minimum energy as possible. So anyway, so once they complete their energy level by picking up an electron from somewhere else, they complete this shell with 8 electrons, and they become stable. And that is the reason they are so reactive. It's easy to pick up an electron. Okay, but nevertheless, the fluorine picks up electrons a lot easier than further down, and chlorine picks up electrons easier than bromine and iodine and so on. So that is why the higher they appear in the group, the more reactive they are. So here is about the reactivity. It decreases down the group. Now, melting and boiling points, now these are physical properties. Those two, they belong to the physical properties. And look at these arrows here, and look at the melting points and the boiling points. These are degrees of Celsius. For example, melting point of fluorine, minus 220. Of chlorine, minus 101. In other words, if they were solids, when they reach the temperature of minus 220, they become liquid. So the melting point, as we can see, increase down the group, because minus 220 is smaller number than minus 101, which is smaller than minus 7, which is smaller than 114 degrees Celsius. Now we go above the 0 here. So we see the melting point increases down the group. They melt, in other words, easier as we go down the group. And the same trend is always followed by the boiling points in substances. Now here is the boiling points, which means it's the change from liquid to gas. So for fluorine, it changes to gas at minus 188 degrees Celsius. And chlorine changes to gas into minus 29 degrees Celsius. So you see it's below 0. I mean, that is why fluorine and chlorine at room temperature in normal conditions are gases already. Because our room temperature is about 20 to 25 degrees, isn't it? Look at these temperatures, they are below 0. So they change to gases at very low temperature. So they exist as gases here. Now, if we go to bromine, it boils at 59 degrees above 0, which means at room temperature, this must be liquid. When the temperature when we heat it to 59 degrees Celsius, only then it changes into a gas. And iodine only boils at 184 degrees, which is quite high, very high actually. All right. So again, we see that the boiling points increase down the group as we go down the group. It's easier, in other words, to reach forget about that. Now, already we spoke that since fluorine and chlorine have a boiling point which is so low, below 0, obviously they are gases at room temperature. So fluorine and chlorine are gases as elements. When we find them as elements, they are gases at room temperature. Bromine though is a liquid at room temperature. It's a liquid, so this is a liquid, and iodine is actually, iodine I should say, is a solid. And of course, as we go down the group, we would expect astatine to be also a solid, and also the next one, tennessine, must also be a solid. So another important aspect that we see here is that in this group of the halogens, we meet all the 3 states. Some of them are gases. There is one liquid and the other is a solid down the group. And we also see as we go down the group, the state changes from gases to liquids to solid. Also, another trend that we can talk about is about the color of the elements, not the color of the atoms. Obviously, atoms have no colors. But when they are in the elemental state, if they are elements, like fluorine gas or chlorine gas, they have colors. And the fluorine is a very, very pale yellow. The chlorine is a little bit greenish, still very close to yellow, but this greenish yellow. These are not obviously, these colors here are exaggerated, but it's a very pale greenish yellow, the chlorine. Bromine, remember it's a liquid, but it's very volatile. Here it's this word volatile means that it vaporizes very easily. So if we have some bromine liquid enclosed into a little bottle and we close it with the lid, we see that it vaporizes, and above the liquid we see a very, very brown like gas, which is bromine in the gaseous state. It becomes gas very easily. I mean, it changes from liquid to gas very easily. This is what it means, volatile. And in other words, I mean, if we have an enclosed container here, like a bottle when we place some bromine liquid here, very soon here it will become full of gas bromine as well, brown bromine gas. Now, the iodine is a solid. We find as a solid, shiny solid. Maybe I can show you some pictures. But it's also volatile, so if we enclose it again in some box, we're going to see also fumes like iodine gas forming on top of the solid, also vaporizes very easily. This is what it means, volatile. And astatine is also a solid, very dark black, nearly black solid. But you will never see astatine because it's so rare, and it's also dangerous because it's radioactive. Also, if you can see here for astatine, we don't have values for melting and boiling points because it's not very sure. Scientists still study astatine, and we are not sure about those numbers, the melting and boiling point. But we would expect the melting and boiling points to follow this trend. We would expect, for example, the boiling point of astatine to be much bigger than 184, which is the previous one, the iodine, isn't it? And also the melting point, we expect it to be more than 114, higher up, because we would expect these trends to be followed throughout the group, from top to bottom. What else can we say very important about the halogens? I have a little video to show you. Let me show you the video about, just to see their colors and where is it? Oh, here it is. Yeah. All right. Let's see.
Here are the 4 halogen elements: fluorine, chlorine, bromine, and iodine. Fluorine on the left is almost colorless. Next comes chlorine, which is greenish yellow. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid, and iodine is a solid. Even so, they're both quite volatile. You can see the colored vapors, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid, or gas, the halogen elements consist of diatomic molecules, F2, Cl2, Br2, and I2. Fluorine reacts often ferociously with almost everything else. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction with hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion. Now you can see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced. HF, HCl, HBr, and HI. In each compound, the halogen has a valency of 1. All 4 compounds are gases. They're also very soluble in water. Here's water swallowing a jar of hydrogen chloride. Now let's see how the halogens react with aluminium. When aluminium powder meets fluorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed. Once the reaction gets going, it quickly takes on the appearance of a pit of hell. As with the chlorine reaction, there's white smoke. That's aluminium tribromide. The reaction with iodine is just as spectacular. A little warming helps to get things moving, but once the reaction's off, it needs no further assistance. The products of all 4 of these reactions are white solids, and they're all trihalides. Al3, AlCl3, AlBr3, and AlI3. Now, aluminium is a trivalent element, so in these compounds the halogens are all showing a valency of 1. That valency of 1 is also satisfied when the halogen atoms bind to one another in the diatomic molecules with which I started this sequence. Okay, now that's enough because we don't know what valencies are, but I just wanted you to see the colors and how they react with in some instances. But let us talk a little bit about the reactions, a little bit, and maybe you can see these pictures again. You see the halogens, each of them, fluorine, chlorine, bromine, and iodine, they can react with oxygen. In other words, they combine with oxygen atoms to form oxides, which are, in general, they're called halogen oxides. But the halogen could be fluorine, could be chlorine, could be bromine, and so on. And I can't give you a general formula because they come in various combinations of halogen and oxygen. So it doesn't matter. But nevertheless, they do react with oxygen. That is good to know. They react with metals. So the hydrogens react with metals. And in the video you showed how they react with aluminium. They had aluminium and they tried it with different halogens. With fluorine, they tried it with chlorine and bromine, and they formed these tribromides and aluminium tribromide and so on. So yeah, you see, with metals, not just aluminium, they react with metals and they form compounds which are called metal halides, and their formula again depends on what type of metal it is. For example, if they react with sodium, which is from group 1 element, if they react with sodium, we would get sodium, for example, sodium halide in general, 1 and 1 here. If this X, the halogen, is chlorine, which is very common, the compound would become sodium chloride, which is the famous table salt. The salt that we use is supposed to be sodium chloride. But it's not only chlorine, all other halogens react with metals. But this is the famous salt that we all know. So this is a metal halide, in other words. It's called a metal halide in general, which are salts. All of these are salts. If you see a metal in halide, these are salts. Another famous reaction, very important, is that they react with hydrogen and they form hydrogen halides,
They form hydrogen halides when they react with hydrogen halides. And again, I will show you when chlorine reacts with hydrogen, and we write it like that, hydrogen chloride, this is called, which is, hold it, let me write it, chloride. And this, if we dissolve it in water, makes the famous hydrochloric acid, a very strong acid, a very, very important acid, the hydrochloric acid. That is why I'm telling you specifically about this one, because it's the base of the hydrochloric acid, which is so important acid, such an important acid in the lab, even at schools. A very strong acid. Actually, all of them form strong acids. All the halides are strong acids, but this in particular is very common. So they react with hydrogen to form hydrogen halides, which dissolved in water form are acids. Yeah, that's enough. You don't need to know anything else about the chemical reactions because we're still very young. But as you go along, you're going to find more about the reactions of the halides. All right. Why do I have the feeling that I forgot to say something very important? I don't remember. Talk about the color, about the state, some gases, some liquids, and some solids. I think that's enough for today, guys. More than enough. In your book, you can also see some uses of these halogens, very important elements, especially chlorine. Chlorine, we find it nearly in all the cleaning agents. We find it in the bleach. We find it in our water to kill the germs. We are very familiar with chlorine. Also, iodine is used. Tincture of iodine, if you remember, we can buy it from the pharmacy, and which is all red, and we can put it around our skin if we have scratches to kill the germs again. So overall, they're poisonous, and especially the first two gases, because they are gases and they're dangerous if we breathe them. But they also kill germs, and that makes them quite useful. And in fact, chlorine gas is used sometimes in wars, and it's a terrible, terrible chemical weapon. And I think we need to stop here. I see a message here. What is this called? But I don't understand, sweetie. What do you mean, what is this called? Where are you referring to it? If you can give me some more details, maybe we have time to answer this question. Or else we have to stop, because another session is coming up as well. Okay, Shakir. It's fine, you said. Okay, great. So guys, roughly this is all about the halogens, and next week we can talk about the noble gases, and we are finished with the groups. Then we'll start the periods with the periodic table, okay? So sweeties, you keep well and have a great weekend. So we're going to talk about the noble gases today, which is the last of the groups that we want to say a few things about from the periodic table. And where are the noble gases in the table? It's the column marked 8 or 18, the last column in the periodic table. Now, they are kind of a remarkable group, those noble gases. Why? Because look at this. Where do we find them in the periodic table? They're in between the most reactive groups. For example, they're in between group 7 here, which are the halogens. And on the other side, which is over there, we go over there, is the group 1, with the alkali metals. And these two groups, group 1 and group 7, which are enclose the group 8 of the noble gases, are the most reactive groups. And yet, the noble gases at group 8 are the most unreactive elements in the periodic table. So here we find this is the most important characteristic of this group. They are the most unreactive elements. And that is why we call them noble gases. Noble in the sense of they are very snobbish, they don't want to associate with any other elements. Very unreactive. And because they are so unreactive, we usually find them we find them as gases, monatomic gases. In other words, gases that are made out of atoms of of whatever element we are talking about. So the first element, the first in the group, is helium. And probably you have heard of helium because it's very common to find it in balloons. Sometimes they fill balloons, and these balloons that fly up. Why do they fly up, these balloons? Because helium is a lot less dense than air, so it goes up. Then the next noble gas is neon. And perhaps you know from the neon signs with these colorful lights. I'll show you a video on that, how they make these neon lights. They're called neon lights, but they are not just neon. They can be any of the noble gases, because each noble gas, actually, when we place them in this type of tubes with some electricity at the two ends, they glow with different colors. So we use, depending on which color we want, we use a different noble gas. So neon is the second noble gas. Then it's argon, krypton, xenon, and radon. And this one is one of the latest that have been added to the periodic table. We know very little about this. We can stop at radon, which is actually radioactive. So we don't really find it in everyday life. But the others are kind of, it's not unheard. In fact, most of these noble gases are found in the atmosphere, with the air that we breathe, but they were the last to be discovered. Those elements were the last to be discovered because they are so unreactive, so nobody knew that they existed. So in the first periodic table, when Mendeleev put some elements in order of their properties, the noble gases were not there. Nobody knew about their existence at the time of Dmitry Mendeleev.
Namibia is known for its beautiful wide open landscapes. However, these deserted spaces also pose numerous educational challenges in our country's rural areas. Because of this, many learners are denied access to proper teaching and learning. At EduVision, we believe that education is the starting point to a journey of endless possibilities. It is EduVision's goal to prepare and guide learners in order to make the modern world they are living in accessible to all.